All right, hello everybody. Welcome to EEE 135, Chapter 5, Solar Tracking. Today we're going to talk about DC motors. Now, we need DC motors because this is how we're going to turn the solar panels to do the sun tracking like we talked previously. Now, DC motors are very well suited for solar tracking, mainly because a solar panel can power the DC motor. So you don't need an outside external AC connections or that many more cables, right? DC motors naturally have higher torque at lower speed than their AC motor equivalent, which is good because solar panels can get pretty heavy and we don't really need to turn them fast. So we care more about slow speed operation with very high torque, and DC motors will actually give that to us much better than like an AC induction motor. Kind of like here's a very basic image of the DC motor. You'll have a stator, or let's start with the rotor, right? There's two basic parts. The rotor is the moving part, so this spins with some magnets on it and some wires everywhere, right? Rotor is a spinning shaft with the armature winding, right? Or the rotor winding, we call that. This is typically connected directly to the load, and this spins the fan or the gears, or in our case, we'll spin the solar panel. The stator is an outside shell, which is a stationary housing bolted to the frame or whatever base we're attached to with stator windings. So you have all these windings wrapped around a bunch, right? We're typically bolt this to the ground in a frame. It doesn't move, and all these wires you put current through, it's going to make a electromagnet. So then you'll have two magnets together, and they'll interact and create rotational force. So for now, notice that there's a spinning part and a stationary part, and magnets make them spin. Now, how is a magnetic field in a DC motor operate? Well, the stator will produce a stationary magnetic field that will engulf the entire rotor assembly. So imagine that you'll either through permanent magnets or enough wires looped around to make an electromagnet, you will have a north pole and a south pole magnet, and these won't change. This is different from the AC system where the magnets are constantly moving because of the AC waveform. With DC motors, once you flip that switch on, the outer stator magnets are going to permanently stay north and south pole and not move. Okay. The rotor itself, the middle part, will have windings looped around, and you will put DC current through the rotor to create an inner magnetic field called a rotor magnetic field. And the rotor field will try to align with the stator field, right? So notice if you have a north-south magnet, you put another north-south magnet inside, it's going to try to align the north pole with the south pole here and another north pole with the south pole here. You'll kind of move the wire bundles and the rotor and lock it into position. Okay. So both magnetic fields interact with each other, where rotor assembly will rotate to align the north-south poles together with the stator field. And this is where that torque comes from. At the end of the day, a motor torque is the north magnet aligning to the south magnet. That's all it is. Okay. So how do we produce the stator field first? So remember, that's the stationary side. So you see we have the base bolted to the ground. We have a cylindrical tube, and we can either put permanent magnets here, so literally rare earth magnets or big metal that we then magnetize, and we super glue them or bolt them to this outer shell. And this, because they're permanent, it's a naturally inducing magnetic field, and it's going to, for the most part, stay like this forever, right? It won't change under normal conditions. Okay. Now, there's only so much strength a permanent magnet can give you before it's either too big or too expensive. A lot of times, bigger motors, you're going to instead use an electromagnet where you'll just have an iron core, you'll wrap a bunch of wires around it, and you'll run DC current through it, and then the DC current will then induce a magnetic field, and you will create a magnet for real, but it won't be permanent because when the current goes away, the magnet turns off. Okay, so as long as current's flowing through the windings, you will get a magnet. magnetic field flowing. Okay, so electromagnet uses DC current through an inductor to induce a magnetic field. Okay. Now notice you could put more than one magnet set. So here you have a north and south pole magnet. We could put more. So on the left hand, this is called a two-pole permanent magnet because there's only one north and one south, so there's only two of them. On the right-hand side, we could put more metal magnets here and wrap more wires and have four magnets. Notice we have a north magnet and a south magnet, another north magnet, and another south magnet. And the only difference between the north and south magnet is which way you wrap the wire. You're going to wrap the wire clockwise or counterclockwise. That's it. Or you reverse the current. Okay. So if you remember something about inductors, the whole right-hand rule of current flowing through the wire, the magnetic field flows with the right direction of your hand as you wrap it around. That's going to tell us which way the magnetic field flows. Okay. At the end of the day, for the stator field, the most important thing you need to know is the stator field stays stationary at all times. It's never going to move. Now, look at the rotor. That's the spinning part in the middle right here. This would typically be an electromagnet. Notice you have a metal bar, and you wrap some wires here, some wires there. You got some wires connected. You can induce a magnetic field, an electromagnetic field, an electromagnet inside the rotor, and this will then spin to align with the north-south pole. And as long as we reverse the polarity of the magnets over and over again, it will continuously spin. Okay. So the field that stays stationary at all times is the stator field, and the rotor will rotate and spin to always align with the stator field. The only trick we have to do is we just got to make sure we can flip and flop this magnet over and over again, and it'll continuously turn over and over and over. Okay, and this is where we have the rotor field. I'll be honest, with DC motors, the rotor field is by far the most complicated one because that's the one that moves. Okay, the stator one stays stationary. You flip the switch on, it's there forever. Okay. Since we want the rotor to always spin, we need to make sure the rotor's magnetic field will swap polarity every 180 degrees. So eventually, the magnet will align with the outside stator. Once it aligns, it's not going to move anymore. So whenever it aligns, we got to flop the polarity of it to then it will move another 180 degrees. And once it rotates 180 degrees, we flop it again, and it rotates a second 180 degrees. And as long as we keep flipping the rotor magnet, as we get to our destination, it will continuously spin over and over and over and over again. Okay, and that's literally how a DC motor works. Okay, so yeah, we swap polarity every 180 degrees by reversing current polarity. This will change the polarity of the rotor's magnetic field. It'll go from north to south, south to north, and it'll just flip, flip, flip. Okay. So here's kind of like a good image I like to show is that notice you have a DC power supply. Current's going to flow through into the rotor. Now notice the current's flowing through one coil here. Okay, so we're going to have a magnetic field flowing through this coil. They'll then jump over and go through the yellow coils and it'll produce another magnetic field here, right? And then it'll come out and return to path. So current's always going to be flowing. And the net result is we'll have a north pole at the top of this rotor and a south pole on the bottom. Now you gotta ask yourself what's going to happen. Well, you have a big north magnet on the left. That's your stator field. So what do you think two north magnets are going to want to do? They're going to want to get away from each other. Okay. So notice this arrow moving up. This is the rotor trying to spin away. The north pole, top one, trying to spin away from the north magnet. At the same time, this north pole is going to be more attracted to the south stator pole right here. So it's going to keep wanting to turn. So in that sense, this one is going to want to turn this way. And this one's going to want to turn this way. Okay. The south pole does the same thing. The two south magnets want to get away from each other. So it turns counterclockwise. And the south and north pole will want to get this together and get closer. So it will keep moving. And now we have a clockwise direction. Now in the middle, you can see we're kind of halfway there. We're so close to the south right here. This has a very strong attraction because they're close by. So you're going to get a lot of torque right here. Same thing on the south magnet. It's going to want to go and stop right here. So now we have most of our strength is between the north and south magnet because they're so close. We're almost done. But once this north magnet hits a south magnet, it's not going to want to leave. It's going to stay still. And we don't want that. We want it to keep going. So what do? At this point, we reverse the polarity of the windings here. And normally this was north before, it instantly flips to south. And what's going to happen now? We got two south magnets nearby. It's going to want to rotate away at a very strong polarity. So anytime you have two south magnets near each other, you're going to want to shoot out with really high torque, really high force. That's what you have. And this south magnet right here now is a north magnet. And that's going to want to push away, right? And now you can see we keep having this turning motion. So as long as every 180 degrees, once our rotor crosses over the stator pole right here, we just flip polarity, and then it'll keep wanting to do this 180 flip-flop spinning over and over and over again. And honestly, that's it, right? That's the magic of DC motors. It's just making sure we're flopping that magnet every 180 degrees, okay? So right here, I even wrote rotor field polarity swapped. Notice a current reversal in the direction. So if you look at the current going through, you'll closely notice, look at the current arrow in the yellow going towards it. Look at it going away from it. So you can see the current got reversed inside the windings. Okay. So when we reverse the rotor field polarity, the rotor will travel 180 degrees to realign with the stator. So it's basically, at this point, this third image here is going to keep moving a little bit. And then we're going to kind of get back to the first image, except the windings are opposite directions, right? So imagine that there's 3 more sets of pictures to do the same thing, and we'll eventually get to the original picture here. And so basically, it'll just keep going forever and ever and ever. Okay, yeah, do the swap constantly, and it'll just rotate. Now, the big crutch is how do we flip-flop the magnets, right? That's the hardest part. We know we have to, but how can we physically do that? This is not an AC system, it's DC. DC is going to flow in the same direction every time. Okay, this is where you have a commutators, and this is where the mechanical people got very smart in this idea. You could create a mechanical commutator to mechanically swap the polarities every 180 degrees. The DC current will always flow in the same direction into the wires. We just have to make sure we can mechanically disconnect the wire and put it on the other terminal and keep swapping the terminals over and over again. Okay. Now, how do we do that with an automated process is the next question. Well, they thought, well, the rotor's round, right? Let's even zoom in a little bit. Okay. So we know the rotor is round. And so at the edge of the rotor, we could put 2 metal sleeves, and they're not touching each other. So we got a blue sleeve and a red sleeve. And we'll put some plastic in between or some dielectric. And we'll put these little metal brushes right here. Okay, so they're going to contact this pad at all times, and we can conduct current through it. So these 2 brushes will then be connected to DC power supply. So we will always have positive voltage and current flowing into the right brush and current flowing out into the negative terminal on the left brush. So current will always flow from right to left. Now, as the current flows in, it touches the blue disc, and then we'll electrically connect the wire to the magnet. So the wire is going to flow through here, through the rotor and back, and come out on the red disc. So in this case, we have a counterclockwise flow of current. And if you do your right-hand rule, you're going to have your magnetic field flowing up the page. Okay, so think about magnetic field flowing up here, and then you do the right-hand rule again. On the other side, it's going to flow up as well. So both magnetic fields on the left and right side current are flowing up the page. Okay, so with that being said, we have a north-south magnet here. Now, as the rotor will spin, notice it spins about 60 degrees. You see how the blue disc is still on the positive magnet and the red disc is still in the negative. Sorry, the blue disc is still in the positive brush and the red disc is still in the negative brush. So we haven't lost electrical connection yet. So we're still going to have the same current flowing. But notice the magnet is not pointing north now. You can kind of see the magnetic field is cocked a little bit. So it's kind of going to the up and right. So think of magnetic field flowing this direction. Okay. So the magnetic physically is moving as the rotor moves. Right? But because the little disc is about 180 degrees, we can still let the current flow and we'll still keep the same magnet. Now, let's say it moves a little more. Right? Now look what's happened. As the rotor spins, the positive brush lost contact with the blue brush and now is in contact with the red brush. And additionally, the blue contact disc now is in touching the negative brush. So the current from the loop of wire is actually going reverse, because now positive current flows to the positive brush. It hits the red disc, goes through the red wire first. So notice that the current's flowing into the page. Previously it was flowing out of the page. You see the reverse in direction. And the blue one as well. So you have the bottom wire. This is the same wire right here. Sorry, this wire went in. This one's coming back out. So you can see we reverse the polarity of the current. So what do you think happens to the magnet? Right? Right-hand rule, you got to turn your hand around. Now the magnetic poles got flipped because we contacted two other electrical points on the rotor. And it's going to spin again to where now we are about 180 degrees from our original point, except look at the rotor. Look at the positions of the brush or the disc. The red disc is now solidly on the positive bushing or brush. The blue disc is solidly contacting the negative brush. So current is flowing opposite of the original position, right? So you can see red flows down, blue flows up. Now red flows up, blue flows down. So in essence, this magnet is complete opposite of the first one. The first one, the north is in the top. This one, the north is on the bottom. Right? And as long as the rotor is spinning, the mechanical links right here will always flip-flop the current. Whichever brush is touching the two discs, right? It's always going to flip-flop every 180 degrees. And that's called a commutating action. Okay? I'm telling you, mechanical engineers were really smart with this idea back in the day, in my opinion. Okay? And they actually have a fifth one right here where you could kind of see it even move again back to its original position. Okay? So at the end of the day, commutation is whenever you have these two discs and mechanically you're going to flip-flop the current in the rotor windings. Okay? So which part moves with the rotor? The commutator, which is this little metal slotted disc, are permanently attached to the rotor and moves with it. Which part stays stationary and does not move? The DC power supply of the motor does not move, and the contactor brushes do not move. All that is bolted onto the stator frame. Okay? That way that doesn't move, and then only the rotor moves, and that's where we got our commutating action. Okay? I mean, that's it. If you can understand this concept, this is the hardest part in DC motors. Okay? So we talked about brushes. Let's get a little more accurate with what brushes are and how they operate. Okay, brushes are the device that lets us keep electrical contact with the rotor as it moves. Okay, so what device keeps contact between the external DC source and the commutator? Remember, we need external DC source to create the big magnet in the rotor. Okay, this could be a battery, it could be a second source somewhere else. Okay. The brushes right here are made of conductive material that will be spring-loaded to always keep pressure on the actual disc in the commutator. So there's literally springs that push it in, and the brushes kind of make out some metal shavings, graphite, and they'll always be contacting it. Now, when you move it, there will be friction. Okay, so these brushes are a the biggest maintenance item for any DC motor. This is why people don't like DC motors. It's because you have to replace brushes on a consistent basis. Think of your brake pads in your car. It's the same logic. Anytime you have friction movement, right, you're going to wear them down eventually. So brushes wear down from friction, so they need to be replaced on a regular basis. You might have to replace them every few years. That doesn't sound bad, but if you have 150 motors in your plant, or you're going to have to remember to replace a brush every couple years, you might be replacing a brush every 3 days with 150 motors, or every week. That could get pretty exhausting, and that's why people don't like the brush part, right? So kind of little show a circuit image of a very, very simple motor with just one magnet here, one set of commutator, one set of discs. But in real life, to be honest, you'll probably have more than just one little commutator set. Here, you have multiple of those discs. Instead of having a disc 180 degrees, they actually break it up into like 20 or 30 smaller discs, right? That way, only a small portion of the current flows through the windings, and you get a lot of magnetic strength for a little bit of current. Okay, so this idea of like it for educational purposes, it's nice to see only two of these discs, so you can see exactly what happens with one loop of wire. But in real life, you have a bunch of them and you have multiple loops of wire. Okay, just to let you know the difference. But the same idea is still there. There will be one set of current flowing through here. It's only through one set of windings. Whichever one these brushes contact, that's the active circuit. So example, you see these two brushes at the top right here? There's going to be two more brushes at the bottom. There's a set of windings for the two top ones. Because they're not connected to the brush, there's no current flowing through. That circuit is dead right now. It's inert until it spins and it's going to be its turn. Okay? So that's the inner workings of a DC motor. Like I said, basic things is know that we have a spinning part with a rotor and a stationary stator, and both have magnetic fields. And we just make sure the rotor magnetic field keeps spinning, right? So that the rotor spins and the stator field stays stationary. Okay. Now, this is where we start talking about the operations of motors. All motors have a torque to speed characteristics. It's typically a graph where you have speed on the bottom and torque on the y-axis, right? So all motors can run at different speeds and torques. You can run a low speed for a DC motor. Low speed typically has high torque, and high speed has no torque. It's a pretty inversely proportional rate. The extremes are when you're not spinning at all and you get the maximum torque possible. This is where the magnets really want to touch each other, but you're not letting them because you're not letting the motor move. So you get a really strong pull force. At the highest speed, there's no torque because all of the energy of the motor is there just to keep it running at high speed, right? So you're basically all the power you could put into the motor is there just to keep itself running. Okay, so typically you don't want to operate in these two extremes. You want to operate somewhere in the middle, right? So when do we have stall torque? Stall torque means speed is zero, but we have maximum torque. When do we have no load conditions up here? When the motor has no load, meaning no torque. Basically, the motor is free running. There's no attached load, right? Nothing holds it back, and the motor is literally going to spin as fast as it can. This is actually really bad. If your motor doesn't have any protective functions on it, a DC motor with no load can actually spin itself to death and break itself. So there's one thing I watch out with that. Okay, but the big trick here to know is torque versus speed is inversely proportional. Low speed, high torque; high speed, low torque. Okay, and we can use that when we start talking about turning DC the solar panels everywhere. Now, gotta do some math. The one big thing we always have to figure out is what's the power and the torque and the speed of DC motors. Because you're going to say, I need a certain amount of torque to move the solar array, and I need to do it at a certain speed, so you're going to buy a certain power rating of the DC motor. Now, it's a very famous equation. Torque is always equal to power divided by speed. You've probably seen this somewhere before. Okay, torque is a twisting force applied to a fan or the solar array, and that's the force it takes to start turning. A good example people like is when you have a jar and you want to open a jar, right? It's stuck. So you take your hand and you start trying to twist it. Now, are you doing any work by twisting it? Well, it hasn't opened yet, so you're not physically uncapping something, so no energy or work is done because you haven't moved anything. But are you exerting energy from your body? Yes, because you're trying to put that twisting force. It's just not working yet, right? So how strong you twist to overcome the stuck cap, that's that torque, that twisting motion to undo everything. Now, once you overcome the cap and it starts moving, that's now you're exerting energy and now it turns into power. Okay. So the big trick for that is you can never get power if you're not spinning something, right? But conversely, you can't have power without torque because you need something to start twisting to make the spin happen, right? So that's why they're kind of proportional. Torque is equal to power divided by speed. If no speed, then nothing happens. Okay. So yeah, torque is the applied twisting force. Power is the rate of energy transfer. I mean, I have to say it 1,000 times. Power does not equal energy. It's the rate of how much energy you transfer every second or every hour. Okay. Now, very important to think about. Look at our extreme ends. In the stall condition, how much power is being produced? Well, power is equal to torque times speed. You just rearrange the formula here. Well, power is equal to a very, very high amount of torque, but we're not moving anywhere. We're not doing any work. It's like we haven't opened the can yet. Okay. On the other extreme end, if we have a lot of speed, but we're not putting any effort into doing any work, so there's no torque, we're just free spinning forever and ever and ever. Well, we're not doing any power because we're not changing anything, we're not transferring energy, we're not moving anything, we're just spinning on our own for no reason, right? It's like your car just spinning its tires and you're not moving anywhere. You're not doing any power, you're just sitting there wasting your time. No work is being performed. Okay, so again, typically these extreme edges are not good to operate at. You want to operate somewhere in the middle so you get a decent amount of power for the torque versus the speed you want. Okay, so very common when you're reeling DC motors, we're going to have to start calculating what's the horsepower needed or the watts needed to size a motor. So for an example here, we have a DC motor developing 3.56 Newton meters of torque at 1,000 RPMs. What is the horsepower rating of this motor at 1,000 RPMs? Okay. Well, torque is equal to 3.56 Newton meters, and Newton meters is the SI unit, so you can keep that, right? Speed is 1,000 RPMs. RPM stands for revolution per minute. Now, RPM is not an SI unit, so you cannot directly relate RPM to Newton meters and to watts. Even horsepower is not a SI unit, it's really watts. But in America, we use horsepower. 1 horsepower is equal to 746 watts. So if you remember physics, we're going to do some conversion. First thing we should convert is speed. We need to get away from 1,000 RPMs. We really should go to radians per second, or this omega. So omega is equal to 1,000. So RPM is 1,000 revolutions per means divide 1 minute. So 1,000 turns per 1 minute of time passed by. Now, we want to get away from revolutions and go to radians. We know with the unit circle, every time you go a whole circle, that's 1 revolution, and a whole circle in a unit circle is 2 pi radians, because it's 2 pi is part of a circle circumference. So 2 pi radians is equal to 1 revolutions. So you put 2 pi radians in the top, you put 1 revolution in the bottom, the revolution units cancel out. And then 1 minute, you need to turn to seconds. So you know 1 minute is equal to 60 seconds. So you do 1 minute divided by 60 seconds, actual equivalency, and you can cancel out the minutes here, and now all your units add up to radians per second. And then you just number crunch this on your calculator, you can get 104.7 radians per second. Okay, so that's our speed of the motor. Now, calculate the power, it's just basic formula multiplication. Power is equal to torque times speed, so that's 3.56 Newton meter times 104.7 radians per second. Number crunch that, we're going to get 373 watts, or if you use this formula, you convert it to half a horsepower. So you're going to go buy a 1/2 horsepower motor for this application. Okay. So that being said, Now is a perfect time to take our 15-minute break. Well, I want you to do a calculation and exercise the size DC motors for solar tracking. So we have a DC motor we need to buy for a solar tracking system. The speed of this motor needs to run to turn at 600 RPMs, and we require 10 Newton meters of torque to turn the solar panel at that 600 RPM rate. When we buy a motor, what is a horsepower rating for the motor at 600 RPMs? So do the same, very similar to what we did just now, except I'm just asking a different thing. Take that 15-minute break, do your number crunching here. Let's come back with some horsepower ratings, and we'll check our work and keep on moving. Okay. So with that being said, pause the video, and we'll see you in a little bit. All right. Hello, everybody. Welcome back to EEE 135, where we're finishing up Chapter 5, Solar Tracking. I come back for a 15-minute break where we actually decide a DC motor for solar tracking. So let's see how we do it. So here we said torque needs to be 10 Newton meters to turn the solar panel. We at a speed of 600 RPMs. Obviously, we're going to have some gearing to make sure that the solar array itself doesn't turn at 600 RPMs. That's why we can have low torque. We just put like a 100-to-1 gearing ratio to multiply the torque and slow the speed down so we could move that big giant metal structure. Okay. So let's convert the speed of the motor itself. Well, remember, we're given RPMs. We need to go to ratings per second. So 600 revolutions over 1 minute is RPM. You multiply by 2 pi ratings over 1 revolution to cancel revolutions, then multiply by 1 minute over 60 seconds to cancel out the minutes. Number crunch all that is 62.83 ratings per second. Right? So now we can just figure out our power. We know torque, we know our speed. So 10 Newton meter times 62.83 ratings per second is 628.3 watts or 0.84 horsepower. So most likely you're going to round it up to 1 horsepower and just buy 1 horsepower motor, right? You also probably buy a 3/4 horsepower motor, but that's not going to be enough, right? So if you ever try to buy a motor that's undersized, meaning less than the required horsepower, when you try to turn it on to actually spin everything, it's not going to do anything. It's going to sit there and just plug and chug and whir a little bit, and then you're just going to break it. It's going to basically overheat and just die. Okay. So definitely want to make sure you're sizing the correct motor for the correct torque application. Otherwise, you're going to just be wasting money and buying new motors again, right? Which obviously you don't want to. Okay. So we got an idea how the magnetic fields work. We see just basic torque power calculations. Another important part of DC motors is we need to figure out how to wire the actual stator fields and the rotor fields. All that needs to go to a DC power supply. So we're not talking about magnetic fields as much anymore, more of a just what connects to what to make the motor run. Okay. Now, you're going to have one external power supply to power both the rotor field and the stator field. There's no point in having separate. They all come from one power source. Okay? But we can choose, do we put these coils in series and parallel, or some more complicated circuit with some added benefits and drawbacks for the type. So very small DC motors typically have permanent magnets, but the ones we're going to order for the solar tracking, the bigger ones, are going to always use the electromagnets. So on larger DC motors, permanent magnets are too big and too expensive. Instead, we run current through a coil to induce electromagnet. There are 3 types of setups we can have. The simplest one is you have one DC source, and you just run current through the series field, or the field of the stator, and then run through the field of the rotor itself through the commutator. So this is a series wound DC motor where the rotor and the stator field are both in series. Now the big thing you need to pay attention here is that both share the same current. So if current raises, if you increase the current, you're going to increase the strength of both fields. So if one field draws more current, it's going to kind of slingshot the effect for the other one to get more current as well, which does have some effects on the way the motor runs. An opposite version is the rotor and stator windings in parallel, where this is a shunt wound DC motors. In this case, the voltage is going to be the same across the 2 fields or windings no matter what, but the current could vary. You could get a lot of current going through the rotor field, but very little amount of current going through the stator field, and vice versa. So they're kind of like they're independent now. They're not linked together. There's some good things, but there's some bad things because now you don't have any feedback between the two. There's no control between the two, and there's some issues with that as well. Lastly, what you can do is you can have a series and parallel called a cumulative compound DC motors, where the stator winding is split into two separate windings, where half of it is in series and half of it is in parallel with the rotor windings. That's why it's called compound. You're kind of getting both the best worlds and kind of mitigating the bad parts of both of them. So it's kind of the middle ground solution. Okay. So just remember when we look at these images, the circular orange thing, that's the commutator where the DC rotor is, the DC winding is. The big coil, inductor coil, that's always a stator winding, the stationary one on the outside. Okay. In this particular, again, the DC compound motor, we're just splitting the stator windings into two separate connections, right? They're still physically in the casing. Electrically, we're just splitting them up. So like in reality, the stator field might have 100 turns of wire to make the magnet. We'll split 50 of those turns on the series one and 50 of them on a shunt one. That's very easy. You just make a couple more connections and nodes, okay? So let's talk about each one, the pros and cons. So first one is series wound DC motor. Stator field wire is wired. This stator field is wired in series with the rotor commutation circuit. Okay. So how are the currents in the stator field related? They will always be the same, no matter what. What's the advantage of the setup? High starting torque. Whenever we need more power, the magnets will say, if you want more power, I need to be stronger. And the magnets will say, to be stronger, I need more current. So at starting, we're going to draw a lot of current through the rotor winding to create a very strong magnet. But because we're forcing current through the rotor windings, we're also going to force a current through the series winding. So we'll kind of have a double up effect of two very strong magnets. It's very good for very heavy loads like cranes, conveyor belts, right? If we have a very, very big solar tracking system with like that weighs 1,000 pounds or something crazy like that, this might be good as well. Okay, what are the big disadvantages of the system? Is a positive feedback system. When one field gets bigger, it makes the other field get bigger. When a second magnet gets bigger, it's going to kind of force the first magnet to get bigger, and it's going to keep growing on itself and ping-ponging back and forth. There is no way to stop this easily. That's why it's a positive feedback system. Okay, the only way you can really slow this down is you got to make sure the motor is loaded enough where most of the energy is then put to the motor, to the load, not to speed the thing up. Okay, so what are the big disadvantages? It's a relatively dangerous system with a positive feedback system. It will destroy itself if ran at no load conditions. So you never want to turn this on, disconnect it, it will spin stuff to death. Okay, that's the big problem with the series wound motors. A much safer alternative is a shunt wound motor where the stator fields are wired in parallel with the commutator field. So the rotor field's right here, the stator field's right here, they're completely parallel. How are the currents related? They're not related at all. They're completely independent of each other. They share the same voltage, but the impedance of this winding and the impedance of the inductor will change based on how strong or weak the magnet will need to be. So this is an ever-changing impedance on these two elements. Because they share the same voltage, if one impedance is low and one impedance is high, they're going to be different currents, but it doesn't matter because the current is independent of each other. They're both coming from the source, and the source can put whatever current you ask for. Okay? So field current, yeah. So in terms of how much current, field current is typically proportional to the torque needed, right? What's the big advantage of this setup? Is very consistent. It's very reliable, right? Torque and speed characteristics are very safe. You don't have to worry about breaking it, and it's overall a safer alternative. What's a big disadvantage is low starting torque, right? It can't power strong loads because you don't have that positive feedback effect like you did with the series motor. So that's the big trade-off. Is it's very safe but weak. So do you want a very strong unsafe motor, or do you want a very weak safe motor? It depends on the application. All right, dangerous motor, as long as you never drive it to the danger point, is a very good motor, right? So I mean, they're both are good in their own world. Now, of course, what we could do is we could get both the best worlds, right? So a compound wound motor, DC motor, is where the stator field is in parallel. So this shunt field, that's the stator field, F1 and F2, that is in parallel with the rotor field. And we have a second set of wires wrapped around the stator, and that's a series field as well. So what ends up happening when current is forced through the circuit, the shunt field and the rotor field are independent 100%, but the series winding here is still dependent on the current pulled through the rotor and the shunt field. So there's a positive feedback effect where this current through the series field will get stronger as the magnetic fields of the rotor get stronger as well. But it's not 100% feedback because some of the stator field is left out because we have a shunt field. So I like to think about it, it's a hybrid motor of the two previous one where 50% series, 50% parallel. What's the big advantage of this? Well, it keeps the high torque of the series motor because you have your series wound field, but at the higher speed, the shunt field will slow it down to where it won't blast into oblivion and have a complete positive feedback system, right? So as a high torque and constant torque speed characteristic, there's no danger of it really blowing itself up. This is kind of both the best worlds. Of course, what's the disadvantage? It comes with complexity, right? This is a lot more complex because now you have two stator feet windings, a lot more wiring involved, there's bigger casings, and it costs more, right? So that's the advantage. That's the problem you pay, or that's the tax you pay is more complexity and a more expensive motor. Okay. And there are arguments for all three. Some people want to save money, they go for a series wound motor. Some people don't mind spending the money, they'll go and get this compound wound motor. Me personally, I probably stick with the compound motor. I don't mind spending an extra 10 or 15% to be safe and still keep about 50% of the benefits that a series wound motor would be, right? So everybody's different. Your boss might be different. Your client might be different, but these are the options you have. Choose the best options for the application and the client that you talk with. Okay. So that's basically the three windings of a traditional DC motor. There's one more type of DC motor we need to talk about. It's a relatively newer one. It's called the DC stepper motor. Okay. A stepper motor, instead of spinning all the time, will spin to a certain position and stop. Okay. So think about something that always points north, and you could press a button and the DC motor will force it to go, and it'll point to this way. You can hit it again and it'll point more down to another 90 degrees. You can hit the button again and it'll rotate this way, and it can rotate so on every 90 degrees. So basically it's a DC motor. Every time you hit a button, it'll rotate 90 degrees. Okay, and that could be very useful, right? Maybe it's a door you want, an electronic door. You just want it to go open, close, open, close, open, close. We could do that. We could have a button that says forward 90 degrees. It goes forward 90 degrees. We got a second button that goes reverse 90 degrees and it reverses 90 degrees, right? So that's what a DC stepper motor is. Instead of consistently spinning, it'll literally go to a certain degree and stop and lock in. Very useful for robotics, control applications, and solar, because sometimes we want to move only 3 degrees. We can make a stepper motor to only move 3 degrees and stop, right? This traditional DC motor, we'd have to run it for 5 seconds and then stop, right? But this one could just be more instant for if you want a smaller application. So for DC stepper motors are good for solar tracking because it has precision and high torque. Now, what is the downside to stepper motors is it has very low speed because it's not going to be constantly turning. It's going to move and stop. So the speed is obviously 0 when it stops. So if you want continuous movement, do not use a stepper motor. But if you want a robotic arm to move 37 degrees and stop, this is where a stepper motor will help you. Okay. So how does it work? Well, you can have multiple magnets here, and each magnet is a circuit, right? And all you have to do is enable a circuit. Basically, you have a bunch of switches to switch which which circuit is supplied with power. You have A, B, C, D. And so all we have to do is say, hey, let's put a positive voltage on A phase on terminal A, which will give us this red magnet here, and a negative terminal on B, which will also give us a blue magnet here. So we'll do both. So long as we have positive A and negative B connected, we have a north-south magnet on the stator. That's the outer ring. And inside, we could put a rotor with an electromagnet, but this time the rotor doesn't change. It's a permanent magnet forever. And the rotor will always align to the two stator magnets we have activated. So AB gives us a top-down position. Now let's say I want to rotate 90 degrees. I would then disconnect B and A phase and rewire my DC source to C and D, which will activate the two horizontal magnets immediately. So immediately turn off the top two, immediately activate the horizontal two, and then the magnet will snap 90 degrees to align with the other two magnets. And as long as I keep the power active, the stepper motor will lock into position because the magnets are strong. Okay, and let's say I want to move it 180 degrees. So you see the red pointing to the right. I want to rotate 180 degrees and reverse the direction of the solar panel. I could do that by taking B and C, and notice I reverse the polarity. C was positive, D is negative. I could swap the polarities and make D positive and C negative. All the current runs backwards in the magnets, and it will reverse the polarity to the two outside magnets, and the rotor will flip over to match it. So basically, it's a kind of a think of digital logic gates that you can literally press buttons and have little switches to switch which A, B, C, or D terminal gets positive power and which one gets negative power. And by making these button combinations, you could pretty much make a microcontroller that will say 90 degrees, 180 degrees, 270 degrees, and 0. And you could just literally press button and the stepper motor will go exactly to what position you want. Okay. So how can we achieve this turning on electromagnets on and off? And the rotor will move to new position and hold that spot we just talked about. Okay, so that's the idea of stepper motors, is just using a bunch of magnets and force movement. Okay. Now, the previous image is very simple, where we have two magnets that's exactly 190 degrees apart, and there's only 4 degrees of movement, either 0, 90, 180, or 240, 270. That's not that useful. I want more than just 4 directions, right? So what we can do is we can have staggered tooth rotors. So instead of only having a rotor with one set of north-south magnets, let's have a rotor with 3 sets. So you see you have a north-south magnet here, you have a second one here, and a third one. So this rotor actually has 6 poles. And we'll keep the 4 poles of the outer magnets, we keep it the same, right? So to increase precision control, always have more rotor magnets than stator magnets. And now what will happen is when we turn things on, the closest magnet will align, not just the same magnet over and over again. Okay, so for example, if we have 1A and 1B active, we have a north terminal here and a south terminal here. Notice the rotor's north and south terminal will align. And let's say our solar panel is aimed towards the purple arrow pointing up and to the left. Now, if I want to move it slightly, all I have to do is disconnect 1A and 1B and put the power on 2A and 2B. All of a sudden, these two horizontal magnets will activate with a south and north terminal. But notice that the rotor, what was the nearest on the left-hand side? If this magnet is now south, what was the nearest magnet? It was this north magnet right here on the rotor. It wasn't that far off. You see, this is only a very small degrees. So whenever 2B and 2A are activated, the rotor immediately snaps over, but it's only a small degree, right? Because there's so many magnets in the rotor. Okay? So by staggering the number of tooths in the magnetic rotor, we can control movement by pulsing the stator magnets that will force the nearest rotor magnet to align. So we could literally have a microcontroller to control 1A, 1B, 2A, 2B, and just flip flop and constantly change the polarity of the current flowing to the stator. And we can actually watch the rotor literally clock in positions, right? And if you have a stepper mode, you can literally go, every time you hit the button, it'll move 5 degrees, and you could go 1, 2, 3, 4, 5, 6, 7, 8, and it'll go clink, 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 right? And that's what a stepper motor does. Now, in this case, here's a quick question. If we went from 1A to 2A, so we flipped the polarity circuit from top down to left right, how much did we move? Well, that's a good question, right? Well, we have 6 of these, right? 6 magnets. Well, if you have 360 degrees divided by 6, there's 60 degrees between each pole. So between this top south pole and this north pole, there's 60 degrees, right? But because we have 6 rotors and only 6 rotor magnets, only 4 stator magnets, they don't align, they're cockeyed. So notice that right here in the left image, the vertical stator magnets are halfway between the north and south pole. So when we activate it, the magnet is only going to move half of the distance between the 2 rotors. Okay? And that's designed on purpose. So instead of having to move 60 degrees, we only move half a tooth, and we only get 30 degrees movement. You see? So now we actually have 12 positions. It's not just 0, 90, 180, and 270. It's 0, 30, 60, 90, 120, right? 150, 180. It's a lot more control, and that's very good. We want more precision. So by adding more teeth to the rotor, we could bring this all the way down to like 5 degrees or 3 degrees or even 2 degrees, right? There's some stepper motors that is very, very almost minute changes you can't even see for very, very precise robotic control, okay? So kind of example of how do you, the stepper motor controller, so if you're building it through Arduino controller with a DC external power supply, right? Assume we have a DC step motor from before with 2 control circuits for 1A, 1B is one power circuit, 2A and 2B is another power circuit, and we can flip-flop the polarities between the 2. So there's 4 total combinations. IA is positive, IB is negative, that's one combination. We could flip them around where IB is positive and IA is negative, that's the second combination. Then 2A and 2B, 2A could be positive, 2B could be negative, that's the third one. And you can flip those two where 2B is positive and 2A is negative, that's a fourth combination. So it's a total of 4 different combinations of source configurations you can use. Okay. Now, first off, how many degrees do we move every time we pulse and change one of those polarities on the stator winding? So anytime we change one of these, well, we did it before, it's 360 degrees divided by 6 poles. But remember, the pulse only moves the rotor 50% of the distance. So 1 pulse is 30 degrees. Okay, so then here's my next question. Let's say we have our solar panel. It's connected to a stepper motor. It's at night. We're facing all the way west towards San Francisco. At night, I need to go back and face towards Folsom in the morning. So I need to make sure my solar panel moves 180 degrees back to facing east. How many pulses do I need programmed with my Arduino controller or any controller to make sure the stepper motor pulses 180 degrees? Well, we know 1 pulse is 1 step. We know 180, we need to move 180 degrees. We know 1 step is 30 degrees, so we need 6 steps or 6 pulses. So at night, you're sleeping, you need to program your controller to literally pulse and press the button, figuratively, 6 times. So you go dunk, 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 and then it flips over, and now you're back to facing in the east. Okay. Now, realistically, you probably want more than just 30-degree movement. So you might, instead of using a 12 pulse DC motor, you might use a 48 pulse or a 36 pulse DC motor, a DC stepper motor. So you can look up stepper motors. There's all sorts of these things, but this is a very common setup for any precise control like solar panel configurations, robotics, other things like, I'll be honest, large applications of fans, motors, and refinery are probably not going to be using stepper motors. They're just going to be using regular DC motors, but this is kind of a special application for a DC motor, the stepper motor. Okay. So putting everything together, what's the summary for our DC motors we learned today? DC motors operate via two magnetic fields aligning together. You have a stator field, which is stationary, and you have the rotor field that constantly changes. They always want to line up with each other. That's how you create torque. The rotor field is induced through the mechanical commutator, the two discs, the brushes that attach them, and the external DC power supply to send current in the rotor to always keep the magnetic field activated. So the rotor field will always be chasing the stator field and will always keep having that turning motion of a traditional DC motor. The stator field is induced from a permanent magnet or a DC power supply in the stator windings. So the rotor field is special. It spins with a commutator. Stator field is permanent. You just literally connect the wires to it and just turn on the power. Torque versus speed characteristic of a DC motor is inversely proportional. So you typically torque is on the y-axis, speed is on the x-axis, and it's an inversely proportional straight line. Okay. At zero speed, we have stall torque where you have maximum torque, no speed. At no low conditions, we have maximum speed but no torque because we're not turning anything. Okay. DC motors have three ways you can wind them, and there's three configurations. You have a series wound motor, a shunt wound motor, and a compound motor. Series wound has high torque, but is a little bit dangerous. Shunt wound is safer, more stable, but it's weak. And compound motor is a combination of both, but it's more expensive and more complex. Okay. Stepper motors are the last thing we talk about. These are very specialized type of DC motor that can move very precisely and hold at a new position at very high torque and stay there forever. Okay, so you're going to need a little controller with it, but it's much more accurate than a standard DC motor that just spins and then stops. Okay, so that's pretty much a little introduction to DC motors. Again, when you're going to use solar tracking, you're probably going to be ordering these or be part of the package. So it's good that you know DC motors because you're going to run into them in the solar field most likely. Okay, so that's all I have for today. Thank you for showing up and listening. We're going to come back next week and we're going to probably do the last chapter of solar power, which is the power electronics side, where we talk about charge controls, inverters, and how to connect them to the main power grid and all the pros and cons and bells and whistles that come with it. Okay, so we'll catch you then. For now, have a good week and see you later.